Okay, let's go ahead and get started. So, I just wanted to mention that the first midterm is next Thursday, which feels kind of soon for the first midterm. Um, but I think it's good because we'll just really get the basics down and mastered, and then we'll move into other things. So here's kind of where we're headed over the next couple of days. So today we'll continue talking about collapsing collections, and we'll probably talk about wrappers as well. And then, or sorry, images of functions. And then Friday will be wrappers, and we'll start talking about continuity. And then Monday we'll continue talking about continuity. And through the end of the day, Monday is what will be covered on the midterm. So I think in the like little book of limits and continuity, that PDF that's like through the end of section or chapter. I'm not sure if it's sections or chapters, but section 3. So that's sort of where we're going. Are there questions about that? Okay, sounds good. So I will later this week or early next week, I'll post a practice midterm so you can get an idea of what the actual midterm will look like and have some practice questions to help navigate your studying. And I'll probably also post like I don't want to say like a full study guide, but just like a list of sort of the topics that will be covered as well. Okay, sounds good. So last time we ended with proving a first fact about collapsing collections, and I feel like I really overcomplicated the proof. So I want to just start over with a clean slate, and we'll just repeat the argument, and hopefully it'll be clearer this time. So the thing that we were looking at was the following fact. So we had this thing called the standard collapsing collection using reciprocals. And the fact was that this actually is a collapsing collection. So the standard collapsing collection, which I'm just going to abbreviate as CC, using reciprocals, is a collapsing collection. Okay, so let's prove this. So in order to show that this is a collapsing collection, we need to prove that this set of intervals, the standard collapsing collection using reciprocals, satisfies those two properties in the definition of a collapsing collection, which were the following. So we need to show first, each interval is contained in the previous one. And second, that there's at most one number that's contained in all of the intervals. Okay, so then let's also just recall what the standard collapsing collection using reciprocals was. So I'm gonna let A be any real number. Then the standard collapsing collection for A using reciprocals is the following. So basically we just start with a and subtract 1 for the left endpoint of the first interval, and then for the right endpoint we're going to have a plus 1. And then as we go on, we'll just subtract now 1/2 and then add 1/2. And then for the next one, we'll do 1/3 and so on. And the kth one in the list will be a minus 1 over k, comma, a plus 1 over k. And that continues. Okay, so that's our standard collapsing collection using for a using reciprocals. So, okay, why is each interval, so we just need to prove these two properties. So for the first one, why is each interval contained in the previous one? So I'm just gonna draw a picture for this. So here's my real number line. And somewhere on here I have A. So what I want to prove is that the interval A minus 1 over k, A plus 1 over k, that this interval is bigger than the next one. So it contains A minus 1 over k plus 1, comma, A plus 1 over k plus 1. Okay, so I'm just going to sketch these two intervals. Sorry. I'm going to sketch these two intervals using the corresponding colors. So let's say A is here on my real number line. And here I'll have A minus 1 over k and A plus 1 over k. Okay, so the point here is that the distance here between A and the left endpoint of this interval is just whatever this number 1 over k is, right? So we've just subtracted 1 over k, and same thing here, we added 1 over k. So each of these two distances is 1 over k. Okay, and then 1 over k plus 1, which is the width of the pink interval, that's going to be smaller than 1 over k, right? So it'll look something like this. So this is 1 over k plus 1 in width now. Right, so the pink interval is contained inside the blue interval simply because the like width of the pink interval is 1 over k plus 1, and that is a smaller number than 1 over k, which is the width of the blue interval. Okay, does that make sense? Other questions? Yeah.
I guess I get that intuition.
Mhm.
What do you have to do? I guess I still don't totally clear on what you need to do to turn that into like an acceptably rigorous proof.
Mhm.
You know, like would just doing it that way be considered like a satisfying proof, or do you need to be more?
So I think for me, like a proof is just if I'm convinced.
Okay.
Like, right, so to me, I find the picture to be convincing.
Yeah.
But if you wanted to make an algebraic argument, you could go the route that we went last time, which was like, so how do you prove that one set is contained in another one? You take an element from here and show that it also has to be in here. And so you'd have to go through proving the inequalities and everything like that. Yeah. So I think, yeah, whichever one you're more comfortable with, like some people, the algebraic version like is more convincing to them. And for some people, the picture is more convincing. I think either one is fine. But yeah, I guess, so if you were going to write a proof, you know, the point is that you can hand whatever you've written down to someone else and they can read it and understand it. So probably accompanying this, you should have a couple of sentences describing the picture and sort of explaining what is being drawn here. I just like when I'm presenting it to you, I did that verbally, but, yeah, maybe we can write a few sentences, so. To go with the picture, so, the interval a minus 1 over k, comma, a plus 1 over k has, let's say it contains all points, distance up to 1 over k from A. So since the points in the second interval, the small interval, are distance at most 1 over k plus 1 from A, and 1 over k plus 1 is less than 1 over k, we have that the little interval is contained in the big interval. So yeah, that's like an example of like an argument that you could write down. Oops, I can't even see the bottom of this. An argument that you could write to go with the picture. Okay, are there other questions? Yeah.
Should it be a plus 1 over k plus 1?
Oh shoot, I just like, sorry, in this last line. This is, I didn't even write down 2 intervals, right? So
Oh, I meant like on the number line.
yes, that too. All right. Okay, other questions? Okay, good. So let's argue the second part. So we also need to say why there's at most 1 number contained in all the intervals. So we are in the situation that the number A is contained in all of the intervals, right? So that means that we need to show that there's no other number that's contained in every interval. We'll say A is contained in every interval. So we need to show that no other number is contained in every interval. Okay, so what I'm gonna do, again, I'm gonna draw a picture. So here's A. I'm gonna take any other real number that's not equal to A. So let's call it C. So if C is contained in every interval, then it's also true that there is no interval that does not contain C, right? So if I can come up with an interval that does not contain C, then that tells me that C is not contained in every interval, right? Sounds like some kind of parable or something when I'm saying it out loud. So here, I'll write it down. So want to show that there is some interval not containing C. Right, so if I produce for you this interval, then that shows me that C is not contained in all of the intervals, because we have an example of one that does not contain C. Okay, so what are we gonna do? So here's the strategy. We know that the intervals sort of just include numbers based on their distance from A. So we just need to find the one whose that is distance that's closer than C is to A. Does that make sense? So this distance is C minus A. Yeah, so I need to come up with a number n such that 1 over n is less than C minus A. So I need to find some number n, so an integer, such that this distance, 1 over n, is less than C minus A. Okay, so that means all I need to do, so I'm just going to flip around this inequality. So from this, what I'm looking for is a number n that's bigger than 1 over C minus A. Does that number exist? This like goes way back to day one when we were zooming out on the real numbers, right? So no matter what real number I have, I can always find one that's bigger. And I guess one thing we didn't say is that you can always find an integer that's bigger. So let's say, let's say my real number that's bigger than this is like 1,000,000.537, blah, blah, blah. So it has some like decimal stuff on the end of it. I can just round this up to 1,000,001. And 1,000,001 will be an integer that is bigger. Okay, so I'm just gonna let n be such that this inequality holds. And then now I have my interval, right? So I have this huge number n, and then that means that the number 1 over n will be less than C minus A. So if I go back to my picture, then if I look at A plus 1 over n, A minus 1 over n, that interval will exclude C because it has width 1 over n. So let me finish writing my proof. Then C is not an element of the interval A minus 1 over n, comma, A plus 1 over n, because the distance from A to C is C minus A, which is larger than 1 over n. Okay, is it making sense? So this, sorry, I have to figure out how to hide my doc on this so you can see the bottom of the screen. So this proves that the standard collapsing collection using reciprocals, it's a mouthful, for A is in fact a collapsing collection because it satisfies those two properties. Okay, let's prove a few more facts that will help us. It'll just give us more tools to show that things are collapsing collections. So, okay, so here's another fact. And I'm gonna call this one subsets. You'll see why. So basically what this is gonna say is that if I have a collapsing collection, and then I have another set of intervals where each interval in my new collection is contained in the corresponding interval in my collapsing collection, then the new thing is also a collapsing collection. So let's suppose C1, C2, C3, and so on is a collapsing collection. And then let's also suppose that D1, D2, D3, and so on is a collection of intervals satisfying the following two conditions. So first of all, we want that each of these D's is smaller than the previous. Right, so D1 contains D2, D2 contains D3, and so on. And second, let's also suppose that C1 contains D1, C2 contains D2, C3 contains D3, and so on. Then the conclusion is that the D's are a collapsing collection. Okay, are there questions about this statement? Do we believe this? Basically, it's saying like if C is a collapsing collection and then I take a collapsing collection that's like smaller in this sense, then that's also going to be a collapsing collection. So, okay, so why is this true? Okay, so why is the first condition about collapsing collections satisfied? Yeah.
So,
Yeah, it just says so, right? We assumed that D's already satisfied this. So, so this is, so one, the first condition for collapsing collections is satisfied. The way that I would say this is like by the hypotheses on D, right? This is like some hypothesis that we assumed about our collection of intervals D. So, by the hypotheses. Okay. Why is the second thing satisfied? So at most one number is contained in all of the intervals. Yeah.
If C is a collapsing collection, then it satisfies that it goes to one number, and if D is always smaller than it also has to go to one number. It couldn't be one.
Yeah, exactly. Yeah. So like let's just think through this. If D contained another number, right? Well, the D's are a subset of the C's, so that means that the C's would also contain that number, which contradicts the fact that C was a collapsing collection. So, here I'll just write since C1, C2, C3, and so on are CC, they contain at most one number. So the D1, D2, D3 also satisfy this. Okay, do we find this convincing? Other questions? Yeah.
I have a question. So if you were like looking at a question on the test and it's like shows you a collapsing collection and it's like prove that this is a collapsing collection, didn't you just like write like that? Yes, it's contained in the set previous to it, and like yes, there's only one number contained in all intervals, but like couldn't you just write that, or did you have to like explicitly go through like drawing this number line and writing like all these like A minus one over K stuff?
Yeah, I think it just depends on what the collapsing collection is. So like, for example, here, I'm gonna go forward. So one of the examples that I have written down for today was like, -1 to 1, -1/2 to 1/2. So this is gonna be factorials, so 1/3 factorial to 1/3 factorial, -1/4 factorial to 1/4 factorial, and so on. Have you guys encountered factorials before? You've seen it? Okay. So right, so like, why is this a collapsing collection? It definitely looks like one, but maybe it's a little bit harder to argue. Yeah, so like why? So I guess we could probably use an argument similar to the earlier one, like to draw a picture and say that like this is contained in this. And then to show that there's at most one number contained in all the intervals, we'd have to like go through what we did in the last proof again. But we're gonna have better tools. We're like proving things right now that will like make this a lot easier. Right? So for example, like you could argue with the thing that we just proved about subsets, right? This is a subset of -1/3 to 1/3, right? Because 3 factorial is bigger than 3. And so you could conclude that this is a collapsing collection from the facts that we just proved. I don't know if does that answer your question?
Yeah.
Okay. Yeah, so this is good. This is an example of like how that fact might be used. Here's like another one. So we had the standard collapsing collection using decimals, which we also haven't yet shown is actually a collapsing collection, but now we can do that. Okay, so the standard collapsing collection using decimals is a collapsing collection. So to prove this, let's combine the two facts that we just proved. What are the two facts that we just proved? The one about subsets that we just saw, and also the fact that the reciprocals collapsing collection is a collapsing collection. Right, so does the standard collapsing collection using, okay, so here's the strategy. So we're gonna use the fact about subsets that we just proved, this one. And the two collapsing collections that we'll be comparing will set C to be the collapsing collection using reciprocals and D to be the collapsing collection using decimals. So with and the D's will be the standard CC using decimals. Okay, so to do this, we need to show that these two hypotheses are satisfied, and then we'll have the conclusion that the D's are a collapsing collection. Right, so for the first one, I'm gonna call these 1 and 2 again. So let's write out the standard collapsing collection using decimals. So I'm gonna let A be a real number. Then we're looking at A minus 1 over 10 to the 0, A plus 1 over 10 to the 0, A minus 1 over 10. Did we start at 0 or 1 with these? I'm gonna have to look at my notes. I think we started at 1, so. And so on. Okay, so why do we have these containments? Like, why is this interval always, why is an interval always contained in the one that came before it? I think we can make a similar argument as before with the drawing, right? So if we have A, and this is our real number line, then the big interval will be given by A minus 1 over 10 to the K, A plus 1 over 10 to the K, and the little interval will be A minus 1 over 10 to the K plus 1 to A plus 1 over 10 to the K plus 1. Right, so the blue interval contains numbers that are distance at most 1 over 10 to the K plus 1 away from A, and that is a tiny number compared to the width of the pink interval, which is 1 over 10 to the K. Okay, so I think we're okay with this one. So then why, so now we need to prove the second thing, that each D is contained in a C. So let me write out what we're proving here. So we need to show that A minus 1 over K to A plus 1 over K, that this contains the interval A minus 1 over 10 to the K up to A plus 1 over 10 to the K. Okay, so why is that true? Yeah,
That's just like the one A is always gonna be a smaller fraction.
yeah. So if we wanted to compare right? 1/k is larger than 1/10 to the k, right? So that's why this containment is true. Okay, so now we have that this was sort of like a quick version of the proof, but now we have that the standard collapsing collection using decimals is a collapsing collection. Yeah,
For the first like part of it, we don't need the number line. Why couldn't we just say that like a plus 1/10 to the k is greater than a plus 1/10 to the k plus 1?
yeah,
And that's all.
Yeah.
So that's all we need.
yeah, you could also say that, yeah. Okay, so we're now going to get a fact that I feel like we've been hinting at in this sequence of facts, but what this is going to say is that we can determine whether or not something is a collapsing collection just by looking at what happens to the width of these intervals, right? Because basically we've just been arguing that like if the width of the interval is shrinking, then you have a collapsing collection. So that's what we're gonna write down an actual statement now. Okay, so write down a definition. So I'm gonna let C comma D be an interval containing A. So what this definition is going to allow me to do is to look at intervals that are not necessarily like symmetric around whatever the element A is. It could be like shifted a little bit or something like that. So this is just going to make this like a more powerful tool. Then we're going to call the radius of the interval C comma D with respect to A. This is going to be the following quantity. It'll be the maximum of the distances of A to C and D to A. Okay, so in a picture, let's say this is C and this is D, and then A is somewhere in the middle, then the radius will be the maximum of these two distances. Yeah.
Why the absolute value?
The absolute values are just there so that I can be lazy about the order. Yeah, because like I did write them correctly right? A is the bigger one, so A minus C will be a positive number, and D minus A will also be a positive number. So yeah, but just to, if you didn't want to be mindful about putting them in the right order, you can just do the absolute value. Okay, so that's going to be the radius. And then here's our rule. So this is, I'm going to call this the reciprocal of radius rule. By the way, this statement that I'm writing down is written incorrectly in the book. So if you're reading it and you're confused, that's because it's wrong. So just write down what I'm writing here as the reciprocal of radius. So this book is like new and under development. So yeah, if you notice typos or something, just email me and I'll forward them to Dan, who's writing the book. Okay, so I'm gonna let C1. I'm gonna have a bunch of intervals, a collection of intervals that contain one another. So this is gonna be a collection of intervals all containing some number A. And then I'm gonna suppose that the radii of these C's with respect to A is given by R1, R2, and so on. So I'm gonna let R sub K be the radius of C sub K with respect to the number A. Okay, so R1 is the radius of C1 with respect to A, R2 is the radius of C2 with respect to A, and so on. So this statement works for any integer K that you put in there, any. And then if there is no number larger than every number in the set of the reciprocals of the radii, so 1 over R1, 1 over R2, 1 over R3, and so on. So all this is saying is that the 1 over the radii are getting bigger and bigger and bigger, right? They're exploding. There's no number that's simultaneously bigger than all of them. Then my C1 up to, my C's are a collapsing collection. Okay, so like, here's an example of how this might be used. So earlier I wrote down the one with factorials. Then the radii are 1 over k factorial. And so this set that you're looking at would be 1 over these numbers, which would be just the factorial. So, shoot. So the reciprocals of radii are 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on. So these are just getting bigger and bigger and bigger. And so there's no number that is bigger than all of them. And so that tells me that this is a collapsing collection. So this is just an example of how to use this rule. Does that make sense? Okay, are there questions about that? Yeah.
So just intuitively, it's a thought like, fact that the reciprocals go up to, or yeah, go up to infinity or just increase without bound, however you say it. It's kind of like a conceptual mirror image of the actual distances. So now the reciprocals collapsing to 0. It's like a distance of 0 away from A, whatever.
Yeah. Yeah, that's a good question. I thought there was another fact. Okay, I don't know. So, okay, are we, comfortable with skipping the proof of this? I feel like it's kind of similar to the statements that we've been doing so far. Okay. So then. Oh, okay, I found the fact that I thought we were missing. Okay, so there's one more. So we'll just end today with this last tool. So this one I'm gonna call sublists. So basically this is gonna say if I have a collapsing collection and then I just pick out intervals from that collapsing collection to make a new collection, then the new thing is also a collapsing collection. So let's suppose C1, C2, C3, and so on is a collapsing collection. If we choose any infinite collection from this list, that is also a collapsing collection. So for example, like if we wanted to think about the standard collapsing collection using decimals, so right, let's just write down the one for 0. So this is like -1/10 to 1/10, -1/100 to 1/100, and so on. This is actually a like sublist of the collapsing collection using reciprocals, right? I'm just picking out every, just a few of the terms. So from the reciprocals one, I skipped the first 9 terms and then took the 10th one. I skipped the next 89 terms, then took the 100th, and so on. Yeah.
So you could have used this fact of like sublist to prove that the decimal
Yes. Yeah.
is a collapsing function.
Yeah, exactly. Okay. Are there questions about this? So now you have lots of tools to prove that something is a collapsing collection. So if you get a list of intervals, then you have a lot of options, like the comparison one, or the sublist one, or the reciprocal of radius rule. You could combine those in a number of ways to start with the 2 standard ones and then cook up tons of different collapsing collections. Okay, so let's stop there and I'll see you on Friday. Yeah.
So, I guess, it just wasn't obvious to me why it's like what the proof would be or why the proof is like, so like what I guess what's the, you just quickly describe the intuition for why it's sort of a similar process to prove that the previous thing.
Yeah, so the first thing about collapsing collections is satisfied by a hypothesis, right? We have, let me just pull it on here. That. So that's like the first thing in the collapsing collection. And then the second thing is that there's at most one number contained in all of them.
Yeah.
So this will guarantee, let's put it this way. Let's say there is some number that's larger than all of these. Then 1 over that number, if I take like a plus or minus that will be contained inside of every interval. Does that make sense? So like saying that there's no number larger than this gives you the fact that there's no number besides A that's contained in every interval.
Got it.
Yeah.
So like if there, in other words, like. If there was some, like, yeah, running with that idea from before of how like it approaching zero and approaching infinity or mirroring with each other, if there was some like. Some sort of like stopping point that the intervals stopped at as they were shrinking.
Yeah,
And similarly, there would be some stopping point. Before they get to infinity, so to speak.
yeah, so like if we wanted to draw a picture, like, oops. Like say here's A, and let's say like the reciprocals of the radius, let's say like 100 is bigger than all of them. Then that means that 1 over, or A plus 1 over 100
Yeah.
is contained in all of them, yeah.
Thank you.
I guess it may not necessarily be to the right of A, but like, it'll be at least one side or the other, because of the maximum thing, yeah.
Professor,
Yeah.
I just